Thank you all for being here. We have our topic this morning, which is, as you already know, black holes. We've never done black holes before. And so this will be a first time, a new adventure. And we are happy to have with us Professor Nima Lashkari, who will be taking over here in just a moment. I'm Dave Cederberg. I'm the outreach coordinator for physics and astronomy at Purdue. And I'm happy to be here with you this morning for our current SMAP, Saturday Morning Astrophysics at Purdue. We have some qualified, well-qualified TAs with us, teaching assistants, who will be joining us in Breakout. Our TAs are undergraduates, members of the Purdue Astronomy Club, and the Society of Physics students. And they will be, I'm sure, very excited to meet you when we go to breakout rooms and you can meet and talk to them. So does anybody have a question before we get started? I might add that if you have a question, feel free to unmute yourself or just ask your question in chat. I would expect you to have some questions as we go along, and you're free to add those in chat. The TAs will be monitoring the chat and will bring the questions to our attention. So, okay, well then let's just dive in. I would like to introduce Professor Nima Lashkari, who will be taking over and enlightening you on the topic of black holes. Professor Nima, would you like to join us and take over?
Sure. Hi guys, so my name is Nima. And today we're going to be talking about black holes, and hopefully I will try to tell you guys or convince you guys that black holes are by far the most mysterious objects in the universe. We're going to talk about some of these mysteries, but we won't be even scratching the surface of how weird and crazy these objects are. Obsession with black holes started when I was your age, or even maybe a little bit younger. And I can tell you that a few decades later, they continue to be shockingly weird. And the more you learn about it, the more mysterious they sound. So let's dive in. Of course, we're not going to tell you, we're not going to be able to wrap up the whole story in this 1 2-hour conversation we have today, but hopefully I'll poke you the right way so that you go and read more about them and learn more about them. So does anyone have any questions about black holes to start with? Does anyone know what they are? Do you guys have any questions? Yeah, go ahead. Please stop me at any point if I'm going. Yes. Any questions or thoughts?
I think you should say
well, wait, hang on. Are they make up like the middle of like a lot of like, not like solar systems, but like universes, because of like their gravitational, like their huge gravitational pull and stuff. But like, do they also like, I don't know how to phrase it.
All right, so let me actually, that's correct. So black holes are, they come in a variety of sizes. The most familiar ones are the astrophysical black holes. These are the ones that we're going to be talking about, but there's a whole different class of types of black holes that we will not get to talk about. They could be small, they could be tiny, but we've never seen them, but we think they exist. All right, let's get started. Please stop me at any point. Shall we start, David?
Sure, go ahead and share your screen and start your presentation.
All right. Okay, guys, do you guys see this screen?
Yes, we do.
It's good. Wonderful. So if you have any questions at any point, please stop me. All right. So we're going to be talking about black holes. This image that you see, this is an actual image from the night sky taken by a telescope, a large telescope, Hubble Space Telescope. That was a telescope that inspired my generation. But yeah, we're going to get to that. All right, let's get started. You might have seen Interstellar. This was a movie that was about black holes. And there's one scene in this movie where they are on a spaceship and they're approaching a black hole. So I'm just going to play a minute of that and tell you guys a little bit about it because it's related to what we're gonna be discussing. So let's see. Hopefully, we won't have an ad popping up. There we go. So, all right. Hopefully, by the end of this talk today, you will get an idea of why these images, some idea of some of the why they're seeing the things they're seeing. So this is a spaceship that is approaching a black hole, but the point is that if they get too close, if they're closer than a certain distance called event horizon, they will never ever be able to go back to get out, and they're doomed. So they will, as they're getting close to the black hole, they'll turn on their engines to escape the black hole. So they're turning on the engines to accelerate outwards to get away from the black hole. And it's a matter of life or death. If they don't make it out, they will die.
Nima, can I ask, we saw like swirls of like flowing light.
Yes.
What is that exactly?
Yeah, so actually that's something that we're going to be talking about. One of the amazing things, incredible things about black holes is that they have such strong gravitational pull that it will bend space-time and light around it. So light will start orbiting around it, and they will make these, light will make these weird images. We'll explain some of these images, but there are some funny lights that you, because of the way that images are formed, they depend on the path that light travels. They form these weird images. Anyway, so this is in the movie, they managed to escape and get out there safely. So let's go back to the slide. So this is the picture of a black hole that they're showing in this movie. It's actually based on a simulation that was done. So this picture is very accurate, represented as a representative picture of what a black hole would look like if you were to go very close to it. All right, so let's start with a poll about black holes.
Okay, we have a poll ready here. I'm going to go ahead and launch the poll. We'll give you a minute or so to answer the questions. Nima, bring up the questions.
Yes. So here's a question. Let me see, maybe I should put the poll to the side. Yeah. The question is, which of the following statements are true about black holes? Are there voids in space and they have no mass? Do they have mass and they're just dark? Can you see a black hole? How do they affect the objects around them? Do they suck everything inside?
Okay, people are answering. We'll give another few seconds here before we close the poll. If you haven't answered, go ahead and make a guess. All right, we're going to end the poll. And it seems, Nima, like we're kind of split 50-50 between choice B and choice D. How about enlightening us on the correct answer?
Okay, so let's see. The answer is choice B. So there are, let's go over them one by one. So first one is that, well, black holes have very strong gravitational pull, but they can't suck everything inside. In fact, there is a particular distance away from them called event horizon. They suck in everything that passes the event horizon. So in the movie, the whole point that these guys were scared about was that they were worried that they might pass the event horizon, in which case they'll just get sucked in. But things that are farther out, they can escape. So they try to suck in anything that comes near them, but there is a particular distance away from them, event horizon, where they can successfully suck in everything. Not even light can come out of it. So you can't see a black hole just simply because light cannot escape a black hole. There's no light that can get to your eyes from a black hole, but they affect objects around them. As we will see, we'll show you some real videos from the center of our galaxy, how they affect the stars in the center near them. So B is the right answer. they're not voids in space. The fact that you can't see them doesn't mean that they're voids in space. Actually, this is a very interesting point because, as a matter of fact, what happens inside the black hole is one of the biggest mysteries that we won't have time to talk about today. Nowadays, we believe that there is very likely there is no space or time inside of a black hole, but that's a whole different story for another time. That's what I do for a living. I research this stuff. They do have a mass, so that's why C is incorrect, and of course D is incorrect as well. Do you guys have any questions? So we're going to go over these one by one gradually and talk about black holes.
Nima, I have a question.
Yes.
Is with today's technology and the ability we have today with spacecraft and space travel, is it possible? How plausible is that scene in the movie? Could we approach the event horizon and have enough power to retract and go back home, or is that just purely science fiction?
So that's a wonderful question. There are a few things to keep in mind. First of all, the nearest star from us is 4 light years away, which means that it will take many years, even on very fast spaceships, to get close to a black hole. Another thing that is incredibly interesting, but we won't have time to talk about, is that as you get close to a black hole, your time slows down. So there will be some effects related to that. So at the moment, it's unrealistic, but what is really interesting is that we're exactly at the point where our telescopes are getting good enough where we could take photos of a black hole, images of black holes. And that's something that you might have heard in the media and the news a few years ago. For the first time, we managed to take an image of a black hole. Ever since, there are more images. So at the moment, it lies in the realm of science fiction to build such a spaceship. Any other questions? All right, so we're now going to get started. So what is gravity? Black holes are objects with very strong gravitational pull. Gravity is a force in between every 2 massive objects. Anything that have mass, any 2 objects that are massive will attract each other. Now, if one of these objects is much larger, for example, the Earth, the attraction that the force of the attraction is more obvious on the smaller object. That's why we see an apple falling towards the Earth, because under this interaction, the Earth barely moves. It moves a little bit, but a teeny tiny bit, and you won't notice it. So that's why gravity of the Earth pulls every object. An apple falls from a tree. And it's not this gravitational force is not limited to the Earth and objects around it. In fact, any 2 massive objects will have gravitational force. That's the way that our solar system actually works. So this is, of course, the artist, an image that an artist has created. The distances are not realistic. However, if you go to the link that is on this slide, this is a real-time image of our solar system. Let's remove the comets. These are some comets to just make the picture a little bit busy. So this is the sun. The closest one is Mercury. Then there is Venus. Then this is the Earth. And this is Mars and Jupiter. So let's make them orbit. This is 28th of this is January 2024. This is real time. You see them orbit. This is 1 second on this animation is 1 week. You can make them orbit faster. So 1 second is 4 months. You see them orbit faster. This is Saturn. This is Uranus. So, and this is real time. We've gone already to 2026. You can stop it at any time. You can go to the past, you can go to the future and see where these objects are. The point of this slide, this image, is that here's a question. This is a realistic calculated map. How do the speed of the orbiting speed of objects, planets near the sun, compared to the ones that are farther out? Does anyone have any answer?
Our planets are faster.
The ones that are closer are spinning faster. Yes. So they have to spin faster so that they can form an orbit. If the Earth would spin a little bit slower, it will just fall down and collide with the sun. Exactly, right? So to maintain their orbit, they'll have to spin faster. So that's the point of this presentation, but it's something cool to play with. All right, so let's go back to the slides.
I will let everybody know that we're going to put the link for that simulation in the chat, so you can check it out later if you're interested in playing around with that.
Yes. All right, so the next activity is that we're gonna talk about the notion of escape velocity in breakout rooms.
Okay, so we're going to go to breakout rooms and introduce to you a simulation related to escape velocity. And let's see what you can learn with that.
What I'm going to pull up here is a simulation that we have. Can you guys see my screen okay?
Yes.
Okay, perfect. So
Yeah.
up here, this light blue dot around where my cursor is, that is some mass that is I'm going to hit play here, and it's going to orbit the Earth.
Dylan, before you do, go to the menu at the top where it says both. And select
just show world. Okay,
yeah,
got it. Perfect.
Get rid of that grid.
Yep. So this is a mass that when I hit play, it starts orbiting the Earth. So you can think of this as a satellite or whatever you like. Down here in the bottom left, it has some parameters for how fast it's moving in different directions and how high it is, or the distance it is away from the Earth. If I hit pause and reset here, we see that this mass is 200 kilograms. This pink arrow is the velocity as we defined it, and this red arrow shows how high we have it, or how strong it is being pulled towards the Earth. So what do you think would happen if I changed this mass to, say, 50? Any guesses?
What was the mass before?
It was 200, so I've lowered it by 150 kilograms.
So it would go to Earth.
That might be what you would think, but actually it stays exactly the same. One of the key takeaways is that this is orbiting the Earth. It's not mass dependent on the object orbiting. It has a lot more to do with the mass of the Earth itself, the orbiting body. That's what creates the conditions for. So I could do this again, go to 100, and it would be exactly the same.
And what would happen if the Earth's mass would be bigger or smaller?
Then it would be pulled in. It would have a stronger red arrow here. This red arrow would be bigger, and it would be pulled in faster. So we'd need to actually to have the exact same conditions for speed, we'd be further away. If we move closer, what would happen on that note? Any guesses?
Object is that's orbiting the planet, it depends on the mass of the planet, how far away the object is, and that initial velocity you give it. So let's say we have it at this 50 kilograms again, but we give it that really big kick that we did earlier. What do you guys think is going to happen? Is it going to go into orbit, or is it going to fly away?
Fly away.
Fly away. Let's see. Woo! Yep. So despite having the smaller mass, it was still able to reach escape velocity. We still gave it enough of that initial velocity that it exceeded the escape velocity of the planet Earth and could fly away, right? All right, let's see. Let me try just giving it a little bit of a kick so you guys can see what happens here. Oh, come on.
I think like the mass of the object doesn't matter because it is like really, really small compared to Earth. So, but indeed it's important, but it's pretty small to be.
That is true, yeah. Let me, and you're thinking like a physicist right there, comparing masses of objects and saying, okay, this one is really small, or the effect of this force is really small compared to the effect of this force. So we can assume that this force is negligible and this force is what we need to focus on. You're thinking like a physicist right there. Let me move. Okay, so I pulled up the escape velocity, and I think you guys can look at this equation and maybe get something out of it, right? You see this equation right here?
Yeah.
So it's the equation for escape velocity. See, but notice how, so this M stands for the mass of the body being escaped from. So in this case, that would be the Earth. And this R is the distance from the center of mass. So the distance from the Earth. That involves the radius of the Earth too, right? The equation does not include the mass of the spacecraft or the orbiting object, right? Completely factored out.
Okay, Nima, I think we're done with breakouts. Would you like to share your PowerPoint again, and we'll resume where we left off?
Absolutely. Okay, so let's go back to the PowerPoint. Here we go. All right. Do you guys have any questions? Before we get to the poll, actually, do you have any questions from the breakout rooms and what we discussed, the simulation we saw over there?
Anybody have a question before we do the poll?
All right, so if questions come up, just ask them whenever.
So, Nima,
Magnetic fields affect the orbits. Oh, wow, that's a pretty advanced question. Yes, and no. The reason is this. In principle, magnetic fields and magnetic interactions, they are another interaction, and magnetic fields will affect the orbits. However, in practice, the magnetic field that the sun produces and the magnetic field that the Earth or other planets in the solar system have are just so small that they do not play a significant role on the orbit of planets in the solar system. Having said that, our solar system is not the only, I guess, what would they call it? Solar system in the universe. There are many of different, there are many more stars. There are a lot more out there. And some of these stars, particularly some of these they have stars with a lot larger magnetic fields, and their magnetic fields definitely influence the orbit of planets around them if there are other planets around them. All right, so let's go through that. How can magnetrons turn into black holes? Okay, so I think these are good questions, but it might be a little bit of a distraction from this. I'm happy to tell you guys afterwards, after the slides, how was Hawking radiation. Well, we're not. That's another interesting story about black hole Hawking radiation, but let's not get into it. You added extra mass of magnetron. Okay, where are big brain questions? Yeah, okay, good. All right. Okay, guys. So we'll go through a summary of what we just saw. There are a lot of amazing things about gravitational interaction, black holes, and things like that, but we won't have time to cover all of that today. A lot of that is going to be on you guys to go read up on these stuff and learn more. Let's get to the poll.
All right, I will launch the poll. Nima, here we go. Go ahead and bring up the questions.
Oops. Uh-oh. There's some problem here. There we go. The question is, the velocity needed for a rocket to escape a planet is related to all of these concepts, except the mass of the escaping rocket, the mass of the planet, the radius of the planet. So from the simulation that you just did, there were three things you could play with, right? There was an object, you could change its mass. You start with 200 kilograms, right? You could change the distance, the radius from the planet, right? And you could also, well, you couldn't change the mass of the planet, right? That was something that you couldn't change in the simulation. So what do you think?
The answers are coming in. We've got 13 people responded. We'll give you another few seconds. Make your best guess. Nima, I think the distribution of answers is pretty well even between the three choices. So I'm going to end the poll.
Okay.
And there we go. So by a small margin, choice A was selected most often, and then choice C, and then last, the mass of the planet.
All right. So let's
enlighten us. What's the correct answer?
The answer is A. The mass of the object, the escaping rocket, does not decide the velocity, the escape velocity, the velocity needed for the rocket to get away from the gravitational pull of the Earth or the planet. So this was the way you see this. If you want to go back sometime after our the 1 hour, 2 hours is over, go back to the same simulation. There were three choices you could make: 200 kilograms, 100 kilograms, and 50 kilograms. Change them and see if the velocity that you need for it to orbit or escape changes. And you'll see that it won't. That's one thing. So which means what? In practical terms, it means that if you have a giant rocket that wants to leave the Earth, for it to leave the Earth, it will have to reach the same velocity as the velocity you need to take a ball and throw it up so that it escapes the Earth. It doesn't matter how small or large the object is, the escape velocity is independent of the mass. I challenge you guys to throw a ball high up so that it doesn't come back. All right. Any questions, guys, about the exercise? If not, let's continue. We're going to summarize this again. Oh, actually, no, okay. So to summarize the concept of escape velocity. Escape velocity is the minimum velocity or speed. We didn't talk about this really, but it's independent of the direction. Is that escape velocity is that the minimum velocity you need to be able to escape the gravitational pull of the heavy object. So what is the escape velocity of the Earth? Does anyone know? How fast is it?
11 kilometers per hour,
Per second. 11 kilometers per second. 11 kilometers per hour is not a very large speed, but 11 kilometers per second. 11 kilometers, I don't know if you know miles or kilometers, whichever was more familiar to you, is a crazy velocity or speed. We're going to comment on that. And we saw that the escape velocity does not depend on the mass of the rocket, right? It does depend, however, on the distance from the surface of the Earth. Does anyone know how does it depend on the distance? If I go to smaller distance, if I reduce the distance, does the escape velocity need to increase or does it decrease? Can anyone say it loud? All right, I'll say. So increase, exactly. It will have to increase. And the closer to the surface you get, the more and more it increases, right? So how large is the largest escape velocity? Of course, the escape velocity of the Earth is, we're going to say that in a second, 11 kilometers per second. That's insanely fast. But if I take the Earth and squish it further, like if I put in a thought experiment, if I just take the Earth and just squish it down to smaller size, then the escape velocity will increase because I can have, if I'm on the surface of the object, the radius is smaller. How large is this escape velocity can get? In fact, we're going to see that very soon, that the largest it can get is the speed of light. But for now, what is the escape velocity of the Earth? The escape velocity of the Earth is 11 kilometers per second. This is a picture from Falcon Heavy. If you click on this link, we're not going to have time to do it. You see the launch, and it takes insane amount of energy to reach this escape velocity. So to give you an idea, this 11 kilometers per second will get you from Purdue, Lafayette, to a city in Colombia in just 6 minutes. This is how fast these rockets will have to move to be able to escape the Earth. One cool thing about these videos, if you watch them, is that you will notice that these rockets, as they go up, they don't go straight up. They'll curve around and go like that. Well, sometime I encourage you guys to think about that. Why is that? The answer is not very easy, but you can figure it out. All right, so that's really, really fast, 11 kilometers per second. So we said that as to make the object smaller and smaller, the escape velocity will have to increase. At some point, the escape velocity reaches the speed of light. This is the speed at which light travels. So how fast is the speed of light? Speed of light is 300,000 kilometers per second. It's so fast that it will get you from Purdue to a city in Colombia 70 times in 1 second. So it will go, if it were to go around the Earth, it could go around the Earth several times within a second. So light travels really, really fast. But nonetheless, if there are objects out there that are so massive with such small radius that on their surface, the speed of the escape velocity reaches the speed of light. And as a matter of fact, black holes are precisely those objects. Black holes are objects where they're very massive and their gravitational pull, and they're crunched to small sizes, such that a distance away from them, called the event horizon, the escape velocity reaches the speed of light. And the speed of light is the highest speed in nature. Nothing can travel faster than the speed of light. So if light cannot escape a black hole, nothing can. Right? So black holes suck in everything. Anything that enters the event horizon will forever get sucked in. There is no way. That's forever. It sort of splits the universe into two disconnected universes. Whatever falls in is forever gone, and whatever makes it out is lucky to not get destroyed and crushed in the singularity in the center of a black hole. The whole story of singularity and what happens to the guys who fall in is another thing, but I can tell you that it's not a good fate. That's why those in Interstellar, you could see that those guys were desperate to fire their rockets and get away from the black hole before they cross the event horizon. All right. So if we were to take the Earth and just crush it, how small does it have to be so that the escape velocity on the surface of it will reach the speed of light? Well, that would be the size of a peanut, an inch or two, basically. That's how small you'll have to crush the Earth. So which means that black holes are, for whatever size they have insane mass, right? They're very, very massive objects, but they don't all have to be very massive. You could have black holes with small mass, but very, very tiny size. All right, any questions so far? So we'll tell you about, there's a lot of crazy things that happen inside the event horizon, but that's a whole different story. We'll get to that. Any questions? Let's see, there are questions in the chat, or did I answer these?
Nothing so far.
Okay, we're good. All right, good. If there's a question, please let me know. All right, so we're talking about black holes. Where are they? Can you find a black hole in the night sky? Well, first thing is that you're not going to be able to see it because black holes do not emit light. In fact, not only they don't emit light, but also they suck in every light around them, right? So the black holes are dark, you cannot see them. However, we can see them from the effect and the gravitational pull they have on the objects that orbit them or are near them. So, for example, how many of you guys can identify the Orion Nebula in the night sky? Have you guys ever seen the Orion Nebula? Or the Orion constellation, actually, the Orion constellation is one of the brightest and most obvious constellations. It's an activity for you guys at night, at home, to go find the Orion Nebula. So Orion Nebula is this guy. Here's his, I guess, a sword. This is his shield, and it's a fighter. This is his belt.
So will you hold this? Just be careful.
Oh, and this is, there are 3 stars here, or what looks like star to our eyes, right? The middle one, if you have a small telescope, you can zoom in and look at it. Of course, you don't see something as pretty as this because these images are taken by long exposures. But if you have good cameras, you could take photos like this, literally. Orion Nebula is so pretty. It's easy to see. This Orion Nebula, at the center of it, has a black hole. So they're out there. So this is Orion Nebula, and an image that is taken with a much larger black hole with higher resolution. So what is happening? What are these lights, and what are these, what's going on here? So what happened was that there was a very, very massive star that reached the end of its life. At the end of its life, it exploded. Such a thing is called supernova. So supernova is an explosion of a very heavy star at the end of its life. And then the core of it, there's an explosion. This is what we're seeing, right? The hot explosive gas coming out. But at the core, the core is crushed down to very, very small size, and it forms a black hole. So there's a black hole hidden in the core of the explosion. Any questions? How are black holes formed inside the LHC? Oh no, there are no black holes formed inside the LHC. That's not true. There are no black holes. There was some sort of a theory that they might form, but it's not actually happening. So black holes are out there. This is an example of a black hole in the night sky that you could see it, but there are so many of them out there. There are many, many of them. All right. Oops, sorry, I went too far. I skipped. Okay, so in fact, there's a black hole. There are black holes come in 2 types. The ones that we can see. There are the ones that are formed from a death of at the end of life of a very, very massive star. They form supernovae, or there are black holes that are at the center of every galaxy. The black holes at the center of every galaxy are called supermassive black holes. These are gigantic, they're enormous. At the center of our galaxy, there's this constellation called Sagittarius. This is also something you could identify in the night sky. This is the constellation that the Milky Way actually goes through it. Does anyone know what the Milky Way is? Do you know what it is that when you see this Milky Way in the sky, what you're looking at? All right, that's a whole different story for another time. But what you're looking at is near the Sagittarius A, you see a cloud, right? What you're looking at is you're looking toward the center of our galaxy, and there's like a gas cloud that you see. Anyway, it's a different story. So, but Sagittarius A star this is like just name. It's a name of a place where the exact center of our galaxy is, right? Is where if we recently built a giant telescope called Event Horizon Telescope and successfully imaged the black hole at the center of our galaxy. This is what the image looked like. What you see is kind of a funny ring. Of course, the black hole is at the center. It's not emitting any light, but you see these lights around it. And we're going to explain what is this. It's actually a complicated phenomenon. What it is that light comes around and gets trapped and starts orbiting around the black hole, the same way that you saw we could put an object near the Earth, give it some sort of velocity, and will orbit. Here it's light that's orbiting just outside of the event horizon. Any questions? All right, let's see the chat. How are supermassive black holes formed? Oh, that's a beautiful question. So this is an old story. I started going to college. This was a problem we didn't know, right? There were two dominant theories. Whether the supermassive black hole was there and then the galaxy formed around it, or were they forming as the galaxy was forming? So they are formed in the process of formation of the galaxy, but now that's a whole different talk to tell you how galaxies are formed, but they're formed during the formation of the galaxy. But let me tell you something that is kind of crazy. There are black holes out that are formed in astrophysical processes, like collapse of a heavy star or like some supermassive black holes that are formed during the formation of galaxies. But there are black holes that were created with the Big Bang. They're called wormholes, and they hold bridges that are non-traversable, but they connect you to other universes. But we're not gonna, unfortunately, have time to talk about this. This is one of the reasons I said black holes are full of mysteries. We can only cover so much in this 1 hour, 2 hour that we have here. All right, any questions? Any other questions? All right. So now we get to a demonstration, and we're going to switch to this demo. But before we do that, I want to tell you something. So far, well, everything we've talked about is the way we've understood gravity up until 100 years ago. You might have heard of this guy called Einstein with crazy hair. What he did and what he taught us that was very, very impressive is that he taught us that gravity could be understood as a curvature of space-time. Gravity bends space and time, and gravity should be properly understood not as a force, but curvature of space-time. So we're going to do a little demo for you guys to familiarize you visually with a concept like that.
Is our team ready for the demo?
Getting ready right now.
Cameron, give us a view with the external cam. What's going on? What are you setting up?
All right, so right here we have a sheet of, I guess, not sheet, but flexible fabric right here. You can see it. And we have it stretched within this, what's called again? Embroidery ring.
Embroidery ring, yeah.
Embroidery ring. We have it propped up on these blocks here.
Show them what's underneath. So it's a very flexible fabric. If you push on it, you can see it bends into underneath.
So we're just going to do a few demonstrations here.
We've got our center here, serving as our black hole, so to speak, and an incoming mass approaching it. Oh, there we go.
Kind of goes into a little bit of an orbit. So this fabric represents how the masses curve gravity. It represents how different masses in this fabric of space-time affect the gravity and how that affects the motions of the orbiting objects, the smaller orbiting objects. Notice too that how, as the smaller object comes in, it kind of starts to move the bigger objects a little bit too. So it's feeling the gravitational effects of the smaller object as well, but just a little bit because it's so massive.
Does anyone have an idea of why we have that the smaller balls are actually falling in instead of staying in a stable orbit around the bigger one in the middle? No. So I mean, we're definitely orbiting the sun. We're not falling in, and we just saw in the demo.
Any Anyone? That's a very good question. Does anyone know how to answer that? Well, I mean, in short, it's the same reason that if you give an object some initial velocity, in the absence of friction, it continues moving forever. It will never slow down or anything. But because of friction, objects that move, they slow down. So that's why in our demo, as the object is moving around, it slowly slows down. As the velocity is going down, it just approaches, gets closer and closer to object, and eventually falls. Any questions?
If you give the smaller objects enough initial velocity, like we saw in the escape velocity demo, you can notice that they kind of curve as it moves through the gravitational pull of this bigger object, but eventually it rolls off the fabric. It's escaping the gravitational influence of that larger object if you give it enough energy to begin with. Go ahead. Well, it doesn't follow a straight path. You think I'm not giving it any I'm not imparting any curving motion on this. I'm throwing it at a straight path through the fabric, but it's the bend in the fabric, it's the bend in the gravity that's causing the objects to curve around the larger object.
That's exactly what we mean by, that's a very good point. That's exactly what we mean by bending space. It means that objects, as they are traveling, the object is trying to travel in a straight line, but the straight line has curved because of curvature. So moving on a straight line, the only definition of moving on a straight line is motion, this curved motion. For us, the way we think about this in post-Einstein physics is that the very definition of a straight line is a path that light travels. Now, if a massive objects make light bend, it means that it makes straight line bend, which means that space is curved.
Let's go ahead and move on. We're getting close to the limit of time here. So Nima, I'll pass it back to you if you want to share your PowerPoint and go back to your presentation.
Okay, so that was a gravity, that was a demo that we're trying to demonstrate give you some sort of image as what it means when we say gravity bends space. But to be a little bit more specific, it's helpful to think about this example. So let's say this is space between us and galaxy far out, like far away. In between the Earth, we're standing here on the surface of the Earth and we're looking at this galaxy. In between us and this galaxy, there is a very massive object, say a black hole, that we cannot see. As light comes, some light rays will travel to the left of the object, some light rays will travel to the right, the other side of the object, and they both bend and meet back again. You see both of these light rays. So what you're going to end up seeing is that as you look here, you're going to see an image of this galaxy or star on this side, and image of the galaxy or star here. You see two copies of it. In fact, because the space is three-dimensional and curved, you're going to see a whole ring. You'll see a ring around this because this has to rotate and it will give you a ring. You'll see the phenomenon. You'll see something that's called spaghettification. That's the scientific term we use for this phenomenon of an object that is behind a black hole. So this is what you're going to see. This is an actual image. There's a massive object in the center. This spaghetti, I guess, this circle is a galaxy that was behind this object. But because of curvature of space, as light rays come, space is curved and you see copies of this object around it like this. And it's just a very good demonstration of how gravity bends light and space. Any questions? So there's this simulation that helps you get an idea. So let me explain what this is. In this simulation, there is a heavy object at the center. So ignore all the dots that you see. There's a heavy object in the center. And then this blue object that you wouldn't be able to see is some sort of a, say, galaxy or some sort of light source that's moving passing behind that heavy object. So let's say there's a black hole in the center, you don't see it. There is a light source behind this object that is just passing behind it. What you see is the white stuff. As the object comes from far, right? The white is what the picture you see. And as it goes behind it, it forms this ring. As it is exactly behind it, it gets spaghettified, right? It forms this spaghetti that is called Einstein ring, named after Albert Einstein. So, and that is actually, this phenomenon is responsible for some of these images that when you look at black holes, you see, sometimes you see these pictures where there's some sort of a ring around the black hole, right? In a lot of these simulations, you see rings. This is the reason behind it, right? Light is going around. Now, just one little thing. This is sort of a cool idea. When I first heard about this, I was pretty young and it blew my mind. One of the interesting things to just imagine how wacky, how crazy it is when light goes in orbit around an object. If you were to stand on the surface of a black hole, the light that will reach your eyes would just orbit around the black hole. So the light that is reflected from the back of your head will go around will orbit the black hole and reach your eyes. So you will see the back of your head. And that's just one particular trajectory of one particular light ray. So what you expect is that as these light rays travel, they'll form several copies of these images, and a lot of them are just like behind you, right? That's why in Interstellar or a lot of other simulations, you see these weird light patterns. It has to do with the fact that light just goes in orbit and does all sorts of crazy things. It's a very unfamiliar phenomenon to us. It's hard for us to imagine what does it mean for light to bend and curve. That's why these images seem so exotic, but it's just one of the weird aspects of black holes. You guys have any questions? How much time do we have, Dave, by the way?
I think we should wrap up in about within 10 minutes.
All right, wonderful. That gives me enough time to talk about a bunch of really fascinating stuff about black holes. So here's a question. Let's start with a question. Let's say all of us are now outside of a black hole, and today I decide to sit inside a spaceship and travel towards a black hole, like the one in the center of our galaxy. What will I see and what will you see as you're looking at me? So as I get closer to the surface of the black hole, something crazy that happens is that my time starts ticking much slower than yours. So 1 second for me takes several seconds for you. As I get closer and closer to the event horizon, time slows down even more and more. As a matter of fact, as I get close to the surface of the event horizon, so much time has passed for you that most humanity on Earth probably has disappeared, and the Earth might have just reached the end of its life or whatever, right? And as I reach the event horizon, that moment maps to your eternity in time. So you will never ever be able to see me cross the event horizon. But on my clock, after a while, I'll just cross the event horizon and enter a black hole. This is one sense in which the universe inside the black hole is completely disconnected from the universe outside the black hole. What you see standing outside is that you see me frozen. As I approach the black hole, because my time clicks slower, it will take much longer for you. So the universes are disconnected. But now here's another. So what you see from outside is kind of boring. But the more interesting question is that what do I see as I fall inside the black hole? That's what we're going to talk about in the next slide. This is a simulation of what you see as you fall inside the black hole. Now, there's like a whole bunch of things before we show the simulation, is that there are a bunch of different types of black holes out there. We've included some links to what you would see if you fell into different black holes. Some black holes are bridges to other universes that you could, depending on how your spaceship is, you could enter or you could not enter. There are all sorts of crazy things. There are wormholes. Wormholes are not traversable. They connect two universes that are completely disconnected. But black holes that have spin have disconnected universes that could be connected. So let's just do some sort of, let's start with a simple example. We're going to go over this. As we watch this, I'll try to comment on this. But it's a lot of complex phenomena happens. Let me just first go to the beginning of the simulation. Oh yeah, here. All right, so let's just explain what it is. So there is a black hole here. You already see, let's say this is simulation, right? There's some sort of, say, this is actually our Milky Way, sort of the depiction of it, right? And the light that comes from behind the black hole forms these spaghettis, right? That's what we're seeing. As we, this is also a map of the black hole is in the center, and we are here, and we're trying to orbit this and gradually fall inside the black hole, right? And this is also telling you how your time clicks compared to the time of an external observer. Let's see how it goes. But I just want to warn you, a lot of weird phenomena happen that we won't have time to explain. You will have to go to do a whole undergraduate or graduate degree in physics to learn all about the details of how these phenomena work. And a lot of them are actually related to unsolved problems. So maybe one of you guys someday grow up to tell us more about this. There's so much we know, but there are a lot more open problems, unsolved problems. All right, so let's.
As you fall into a supermassive black hole, you would start experiencing the strong gravitational pull of the black hole. Within short time, you'd be accelerating to speeds close to the speed of light.
So this is the path that your spaceship is.
For your friends that are observing your journey from the outside,
ignore
you
these
see you
red
fall into
lines.
black hole in slow
I can
motion.
explain what they are later, but you do not see
As
them.
you approach closer and closer to the event horizon of the black hole, time would slow down for you.
So the time that you see is this orange clock light, and then the white is the one that the clock for the external observer, your friend outside. So it's going really fast, right? And for you, it's very
your
moving.
friends would ultimately see you freeze at the event horizon. But for you, time would pass normally. As you cross the event horizon, something very strange would happen. If you look towards the center, you will see every object that has fallen into the black hole before your journey commenced. And if you look backwards, you will see everything falling into the black hole behind you. And
so one interesting thing to say over here, of course, you have the links to these videos, you can watch them, but I want to comment on one thing. Just to give you an idea of what goes on, what Einstein taught us is that there's a nice analogy about to help you think about what happens inside the black hole. So for us, we think of space as a dimension. I can move to left, I can move to right. And time is also a dimension, but I always travel towards the future. I cannot go to the past. So time is a dimension that has a preferred direction, right? I cannot travel to the past. I have to go to the future. But space is another dimension. Space are other dimensions where I can move towards left or right, forward or backward, right? Now, what happens inside the black hole as you fall in is that the role of your space and time switch. Your radial direction, which was the direction that you fall in, becomes like time. The same way that in your time, you have to move towards the future. You can't go to the past. as you're falling in, you have to move towards the center of a black hole. You can't get out. So your space becomes like time, and your time becomes space. So they switch. It's one of the nice analogies that helps us, like mathematics helps us, tells us that this analogy is precise. But we know that the story of what happens inside the black hole doesn't quite stop with Einstein. In the 70s and 50 years ago or so, Hawking taught us a lot more about black holes. We continue to learn about black holes. We think it's possible that at least for some black holes, there is no space or time inside it. So that's a whole different story for another time. All right. Now, let's just wrap it up by giving you guys a whole bunch of links. There's a lot more to learn and watch about them. What we talked about today is really the physics of black holes, that as we knew it, as Einstein taught us in early 20th century. We've learned quite a lot about them. Black holes have a lot of bizarre quantum effects. That's a whole different story. There are a lot of beautiful things to learn about them. Here are some references for you guys to learn about them. I can tell you that at the moment, by far, they're the most mysterious objects in the universe. And I'm pretty sure in the future, if you come back, check 20 years from now, they will remain to be the most mysterious objects.
If anybody has a question, unmute yourself or put it in chat.
Here's a time that you can throw out all your questions.
Without any other questions, I would like to thank our Professor Nima for the great presentation. I think my mind is still spinning from black hole, falling into black hole, time becoming space, space becoming time. These are kind of challenging things to think about. So I thank you for joining us. TAs, any final comments? Nima, any final comments?
Thank you so much, guys. I really enjoyed talking to you. And of course, there's so much out there to learn. There are there's a lot of resources, and I guarantee you will not run out of information and interesting resources to learn about online, to learn more about black holes. They're fascinating, they're incredible, and I encourage you to learn more about them. It's been I managed to turn a childhood dream into a career, so I encourage you guys to do a similar thing.
All right, Nima, thank you very much, and thanks you both. We will conclude today's session. Thanks for joining. We'll see you next time in December for the November for the November SMAP. So thank you. Have a nice weekend. Bye-bye, everybody.
Bye.
If the TAs would stick around for a minute, everyone else can go enjoy their day. Thank you.
Thanks, guys.